to talk today about probability dilution, false confidence, and non-additive beliefs.
Okay, well, thanks guys for coming. So yeah, I came in this morning, flew in very early, very snowy, very unpleasant. So I left North Carolina, it was 75 degrees yesterday. So out in enjoying the sun, and then today is freezing, and then delays on the highway and things. But anyway, so still is great to be here. Nice to see some familiar faces and a couple new faces. So today I want to talk about this a couple of things here, maybe some things. There's some words here that are familiar, but maybe this particular ordering of them maybe is not. Something about probability dilution, false confidence, and this non-additive beliefs. Okay, so maybe we can jump right in. So this, for once after I start talking, more people show up. So normally it's the other way. Once you start, the people leave. So this is a nice change. Okay, so let's restart. I want to talk today about some notion of probability dilution, false confidence, and this non-additive beliefs. Okay, so in a statistical inference context, it's really taken for granted, that this uncertainty is going to be quantified using probabilities. And so, I guess Glenn, of course, is very familiar with this, is that, there are other kinds of measures of uncertainty, so other belief functions and maybe some other kinds of things, and all of these are, potentially effective measures of uncertainty, and maybe better in the sense that there's some kind of, these actually have some added generality. So the fact that these things are not so common in the statistical inference context, really would suggest is that we've not encountered any sort of a, quote, crisis as a result of using probabilities. And so here I have a cliffhanger, right? So maybe at least not yet. And so I want to tell you about that's one of the main parts of the talk, is to say something about a context in which there's something really funny going on with the use of probability in terms of summarizing this kind of uncertainty. Okay, so this particular example that I have in mind, this is actually a real example, has to do with how what's called the conjunction analysts. So they're investigating, they basically are watching satellites that are orbiting the Earth. So there's all kinds of satellites for various different kinds of purposes. GPS satellites, maybe cell phone satellites, all these kind of things. So there's a bunch of guys out there orbiting the Earth, and so there's of course a chance that two satellites could collide with one another. So that would obviously, I put here a disaster, right? At least in terms of the people who own the satellites, this would be a disaster because it's a huge pain to get those things actually up there, right? So that's a huge cost and a huge inconvenience for folks here trying to do their GPS navigation from city to city, right? So this may cause some kind of problems. And, so how this actually goes is what these analysts do. They track these satellites and their movements and their, some positions and some kind of velocities and things like this. They track this basically in real time. I don't know, so I guess I should preface this is that I'm not an engineer, so I only know this kind of application at sort of a surface level. So, but my understanding is that they are tracking these things at essentially real time, and what they want to do to, when they're trying to assess whether the satellites might collide, they calculate some kind of probability of collision. Okay, so I mentioned in the title there was this one phrase which maybe is not familiar, what is called probability dilution. This is a sort of an unusual kind of a paradox which says that the noisier data that I have in my measurements of the satellite's position and their velocities, etc., this actually leads to a higher non-collision probability. Okay, so what this indicates is that the worse data, data which is of lower quality actually can give these analysts false confidence, some kind of higher certainty that their satellites are safe, right? And so it's a paradox in that kind of sense, that that worse data actually suggests that we know more about the situation at hand, right? And so this notion of false confidence is this idea, okay, that this non-collision probability is actually large for some other reason than the data actually supports such a conclusion. Okay, so this actually has some kind of some serious consequences, right? So we haven't heard about satellites colliding. This is partly because, I mean, well, let's just say partly because there aren't that many satellites out there relatively. But as we progress over time, of course, they're building new technologies, and so those technologies require some kind of satellites to track things. And so there is increasingly many satellites being launched and placed out there, and so obviously the more crowded it gets, the higher the chance that something actually could happen, or at least the greater the risk. So being able to...
arrow supposed to be obviously plausible to us? Or?
Sorry?
Is that arrow supposed to be something we should...
No, I'm gonna say something about this, but okay, so I'm not saying it should be true. What I'm saying is that this is what's actually happening, is that when you do the calculation, it turns out that noisier data leads to higher non-collision probability. So it indicates...
It's not something with some kind of intuition.
No. So this is the paradox, right? Yeah, so this is this is what's unexpected, and that's yeah.
That's the definition of probability dilution.
Yes. So the probability of dilution is this phenomenon where the noisier data is implying that the non-collision probability will be higher. Yeah.
No, is this true universally? This probability, is this always true of any model, of any statistical model?
I probably can't say that. No. Okay, so what I want to do today is to tell you a little bit more about this, that collision problem and the probability dilution phenomenon. And then, so I want to then try to take this back and ask some more general kind of considerations about inference and about evidence, and what does this say about some kind of additivity of the way of measures of evidence. And in fact, sort of the main conclusion here is that additivity and false confidence are actually tightly tied together. And so then there's sort of this natural thing, well, if I'll argue that, well, false confidence is bad, okay? And so if I want to avoid something bad, what do I have to do? If additivity is connected to this bad thing, then to avoid it, I have to go non-additive. So I'll tell you some things about what do I mean in the sense of non-additive, and then I'll want to come back to this satellite collision example, and then talk about sort of how the conclusions that we can get from looking at this particular kind of a non-additive type of measure, how this actually can provide some solutions to this satellite collision problem that make more sense, that can avoid this probability dilution type of phenomenon. So that's the plan for the talk. Okay, so yeah, by the way, I know that you'll do this anyways, but if you have some questions about something, go ahead and just yell out, is fine. Okay, so I want to talk here first about, I'll give you a few more details about this satellite collision example. So the idea is that, well, they're monitoring, like I said, they're monitoring the position and velocity of these satellites, and basically in real time. From, of course, that's a lot of data, and so what they do some kind of processing, which I don't totally understand all of that, but at the end of the day, they're doing some kind of reduction to a kind of a three space, right? So basically like where these satellites are orbiting, and then they can do some kind of a further dimension reduction to get it down to a two-dimensional problem. And so basically what they do is they can sort of create a sort of a tube in the three-dimensional space, and so if the satellites are sort of in the same tube, then they say that they're going to be colliding. So essentially they're reducing this three-dimensional problem down to a two-dimensional problem. And so here we'll have some things to the bivariate normal distribution, and so because of the way all of these things are put together, I guess the normality assumption has some kind of justification, and there's apparently a lot of data. So the measures of uncertainty in terms of like the covariance structure for these this two-dimensional object, this is something that's taken to be known. Okay, so the setup here is after all of this kind of, there's complicated physics, and then they collect a bunch of data, they do some kind of processing. At the end, it's actually a relatively simple setup. It's a two-dimensional problem that has a normal distribution, unknown two-dimensional mean vector, and a known covariance matrix. And so then when they talk about a collision event, So I should maybe say something a bit more about this. So that two-dimensional thing that they measure, this is sort of like, you can think of this as like the difference in the position of the two satellites. So if that mean vector for the difference is relatively small, then that means those two satellites are close, and that's an indication of collision. Okay, so what we actually are interested in is this mean vector, and in particular, is that mean vector too short? Right. So if if the mean vector has too small of a norm, then that would indicate that the two satellites are close to one another, which is bad. That's a type of collision event. Okay, so it's actually, I mean, a relatively simple model that we get to after a bunch of complicated processing. And so there's some more detail that I'll mention. This is based on some work that's in this paper on arXiv now. So there's some more details about this processing. Those are not really interesting, I don't think. So I left that out of here. So this is more of in terms of symbols, some kind of explanation of what's happening here. So the data I have X, this is like my measure of the position, or the difference of the positions of these satellites. So think of this as like an estimate of that mean vector. Right? And that mean vector I'm representing here by theta, that's some two-dimensional guy. And Z is the kind of random error that's attached to this. So the point here is that we've got this kind of an estimate, and of course there's some kind of uncertainty in that estimate, and so I'm incorporating that in terms of this bivariate normal with a mean zero and a known covariance matrix. And then the object of interest here is this the length of that two-dimensional mean vector. Okay, so what these conjunction analysts are doing now is they carry out what is I mean, they would consider this to be a Bayesian analysis. It's essentially, I mean, also, since we have some confidence distribution folks in the audience, this is also the confidence distribution that really anyone would get for this kind of problem. And it just boils down to a flat prior distribution for this mean vector. All right, so with that kind of setup, then everything is now relatively simple, because now the Bayesian posterior distribution will inherit the same bivariate normal distribution. Just now it's centered, that distribution is now centered on X. Right, so just basically shifting the positions of theta and X, that's effectively what the Bayesian solution will do here. Okay, so now there is a definition of what it means to collide, and this is a constraint, or it basically says that if the norm of this vector is too small, then the satellites collide. And so this S here, I mean, it's not important for us here, but it has something to do with the size of the satellites. Right, so big satellites are going to collide, right, with a relatively large difference versus smaller satellites need a smaller thing to collide. So this has something to do with the size of the satellites. Okay, so then what we said before is that, okay, so the idea is I want to calculate some kind of this non-collision probability. So I've now defined what it means to collide in terms of this mean vector, and I have a Bayesian posterior distribution that's defined on this parameter space. So I can I mean, whether this is an easy calculation to do or not, it actually is an easy calculation. But I mean, there it is. It's a relatively simple type of formulation. I just calculate the probability that the norm of my that mean vector exceeds this threshold S, and this is posterior given the data that I have. Okay, so this is a pretty simple kind of formulation, right? Actually is a very reasonable kind of strategy. So there's something weird that happens. So this is this notion of probability dilution that I want to explain. Yeah, sure.
That's a question about the previous slide.
Yep.
So we have a bunch of satellites flying around, and we're doing pairwise comparison of the mean difference between distances.
Well, okay, so I'm only talking here as if you've identified a pair that might be in collision. So I think what you're getting at is the multiplicity type of correction. Is that was where you're headed? So I don't know whether these conjunction analysts are actually thinking about the multiplicity issue. I don't know. But my focus here is just on a particular pair that maybe have been identified as potentially on a collision course, and then they want to investigate those further, and they can do this calculation for those. So it's not necessarily all pairs of satellites, because some are not anywhere near each other. These are two that have been identified as potentially on a collision course.
And the measurement we do is on X, right?
X is the measurement. So think of this as like I have, I get some kind of data on the position of satellite A,
Right.
and I get some data on the position of satellite B.
Right.
And then I do some kind of processing of this to convert it down into a two-dimensional quantity, and then I look at the difference of those two things. So it's like an estimate of the difference between their positions, right? So being 0 means they're hitting exactly, and being close means they're passing close by. And so then this kind of, the mean of that distribution of the difference really captures the actual position of these satellites at their sort of closest approach. And if that mean vector is sufficiently long, then they're not close to each other. Everything's going to be fine. If they're close, the mean vector is short, right? Then there's potential collision. Right? Okay, so this is the part where something weird happens. So here I just have a very simple example, one that I can draw some pictures of. So the setup here, I just take the S to be 1. It really it's really relative to the sigma. So I've got a simple covariance structure here, just IID. So there's just a common variance sigma squared. So I'm going to let that one vary, and then I'm going to look at several different values of this, the length of my observation. Okay, so this probability dilution here in this specific case, we can see what's happening. This is saying that non-collision probability is, at least eventually, is an increasing function in sigma. Okay, so in this particular case, this is like where where that estimate of the squared length is relatively small, right? And so this is compared now to the S, right? S is 1, right? Or S squared is like what we're comparing this one to. And so S squared is 1. This one is smaller than 1, right? So that means that the data is saying that actually the satellites are close to each other, okay? So this means that collision should be, inevitable in some sense, right? And as sigma gets large, so this is on the log scale down here, but on the regular scale here, once you have large sigma, then the non-collision probability is actually quite high, right? Eventually is equal to 1. Right? And you see that really in every setting, it's of that type. It's that eventually the probability of non-collision approaches 1. Is that the
probability of not collision?
Yes. Yes.
According to your setup on the previous slide, am I to understand that the leftmost picture over here has a norm of a half? Is that right?
The squared norm is a half. Sorry, so this is the data. The data says, the data is, so think of this as like my estimate of the.
So that's not the real position. So
No.
That's
Yeah. So the data says, if I calculate this norm based on the data, it's small. Right, so that actually is an indication that the satellites are on sort of a direct collision course. And what's happening here is that as the data that I have becomes more noisy, I become more certain of the satellite safety, despite that their data actually says they're on a collision course. Okay? And here's just a few other examples of this. So this one is a bit strange. Well, maybe I'll point out this one because it has a very different kind of shape than the other one. So at small sigma values, right? So here the squared norm is bigger than 1, right? So that means that the data is indicating that there won't be a collision, right? Because the estimate of my squared length is bigger than 1, and S equals 1 is the cutoff, right? That says this is when the collision event occurs. So when I have very precise data, then non-collision probability is high, and that makes sense, right? Because I have an estimate which says I'm probably not going to collide, and that estimate has a lot of certainty attached to it because the sigma is small, right? So then I should be sure that I'm not going to collide. Right? But then again, as the noise gets bigger, the non-collision probability goes back up to 1. Right? So this is saying that even though, so I mean, the data is saying that you're not going to collide, but as the quality of that data goes down, you get more noise. Again, the non-collision event is virtually certain. right? So this is strange in that somehow the lower quality data can actually give you more confidence in the safety of the satellites. Right? So this is what I meant by probability dilution, that the more noise you have, the higher non-collision probability you observe. Okay. So in the actual applications in the satellite setup, so of course I just picked some s=1 and some range of sigmas. In the real satellite collision examples, like the actual data that they're collecting, that sigma is actually tends to be large, right? So this situation where I'm showing you, I mean, sort of the bad stuff is happening on the far right side, where somehow you're always being certain that there's a non-collision. That is actually the reality, that the sigma actually tends to be relatively large. So you're in that situation where this false confidence is coming up. So that's the troublesome part of those pictures, is the realistic one. Okay? So what's happening is that, I mean, they're calculating these probabilities which say, yes, there's a non-collision is certain, but that's actually totally meaningless, because what you see is that, from the picture, is that that's really just a result of the noise, not about what the data is actually saying about whether they will collide. Yep.
So these aren't all monotone relationships. So I mean, are you saying that this is like a steady increase with sigma, or is it?
No, it's, I mean, eventually is increasing. So you're saying that if I went over here to 10?
Yeah, exactly.
Let me think about the formula. So what's going to happen is that, so in the formula, this is basically something to do with the non-central chi-square. Everything has, so a few places in that formula, there's a sigma squared in the denominator. And so when the sigma is very large, that's going to kill off everything. And so I think eventually this is going to be, eventually this will be strictly increasing in sigma. And so that when you get out here to like log sigma equals 10 or 20, it's not going to dip down again. Yep. Okay, so this has some kind of serious consequences because of the way they're using this, right? So they're calculating this non-collision probability as a way to test whether there's actually some risk. And so it turns out that basically that it's showing non-risk, but that non-risk is not real. That has something to do with how these probabilities are calculated. Okay, so in terms of what's actually going on here, I think that this is this first part here, well, maybe not so easy to explain. This is actually I think the key point is that if what we were talking about was randomness, or this aleatory uncertainty, then this would make sense, right? Is that two things which have a lot of variance, right? If I look at the difference between them, right, I expect a very wide distribution for this, not something concentrated by 0, and so therefore you would expect that more noise means less chance of collision, right? But that's not actually what the sigma represents in this case. It's not variance of these, it's not this kind of variability that it measures. It's actually measuring the quality of the data that you have. So this is more like some kind of an epistemic type of uncertainty, and so it doesn't make sense that the lower quality data gives us more certainty in the safety of the satellites. So it's something about that probability is naturally capturing this kind of aleatory type of uncertainty, but that's not the actual uncertainty that we want. We're interested in this kind of epistemic uncertainty, which is about whether we think that these things are going to collide. There's no randomness there. They're colliding or they're not. And so I'm not interested in aleatory uncertainty. It's the epistemic type that I'm interested in. Okay, so what I think is actually happening here, maybe to here, it's that, so for certain kinds of sigma, right, especially these large ones, the data is not really all that informative. And so what I don't entirely have a rigorous argument for this. This is sort of basically my understanding, is that when the data is not informative, it's certainly, so for example, like this 0.9. So when the squared norm of the data, of the observation vector here is not 0.9, right? That doesn't support collision. Sorry, did I write that correctly? I think maybe this wording isn't quite right. So it's not really, so when the sigma is large and I observe something like this 0.9, this is not really supporting collision. And because of the way probability kind of works, when it's not supporting collision, additivity sort of forces it to be supporting non-collision. And so that's the sort of why we're seeing this sort of artificially, the probability of a non-collision tends to be large, is because that's anything that's not supporting collision is getting lumped into non-collision. And that's what I'm thinking sort of intuitively is what's going on here with this probability dilution and ultimately this notion of false confidence that I want to talk about. Yep.
You said something about, you were saying that the sigma, the variance, you want it to be interpreted in terms of epistemic uncertainty, but it makes sense more in terms of Alley theory.
Yeah.
I realize that you want to interpret it that way, but to what extent can this sigma be interpreted as an epistemic quantity instead of, since I assume that the model is describing the data and how the data is collected, and mechanism for.
Yeah, so I believe that because there's actually lots of calculations that are going into this pre-processing. So I believe that the normality part is something that has to do with the that there's a central limit type of argument in sort of this processing they're watching this thing on a track, and so they're processing the data. There's actually lots of data getting processed and lumped together. So I think there's like a central limit theorem type of argument that's getting to this normality part, so that at least from what I understand of the engineer's argument is that the normality assumption isn't a question. So the model here is something which is a reasonable model for that processed data as far as I know.
So that means that the variance is like a physical quantity, or it's describing something that's physical.
Yes.
So at what point does it become an episteme, a description of epistemic uncertainty? Or, it seems like you want it to describe that. You want it to describe kind of low-quality data.
Well, it's not necessarily that I want it to describe that. It's that I think that that's the way it's been interpreted, is that this is actually representing the uncertainty about whether there's going to be a collision, and that it's not actually describing that kind of uncertainty. It's
right. Well, I guess, yeah. Is there a difference between it describing kind of your uncertainty about whether there's a collision, or just describing the probability that there's no collision? And that's kind of an objective quantity. I guess if this model is an objective model talking about physical things, and then the posterior probability is just describing that physical objective probability.
I can't say that it's, I think it is describing that objective probability, just that objective probability isn't it's not actually it's not measuring the kind of uncertainty that the engineers think that it is. So I'm not trying to force it to do anything. This is more of an observation that just says that this is something that the engineers have noticed, this increasing kind of behavior, and that this has been confusing to them, and I think maybe I say it somewhere, is that they've made some kind of ad hoc sort of adjustments to these probabilities to try to accommodate this weird behavior, and that somehow it's not been understood really what's going on behind the scenes here. And so this phenomenon is actually not new to the engineers, but how to get around it is the kind of the new part. So I'm not trying to force the probability to do anything in particular. I'm just pointing out this phenomenon. Yeah. Okay. So the natural thing is that, so if you don't like this this kind of probability dilution phenomenon, then what can we do? What I think we want to do is to focus, thinking about what kind of information that what kind of information does the data bring? And so this is really thinking about what is there evidence in the data to support conclusions about like collision, non-collision, or sort of more generally, I have certain kinds of hypotheses, and maybe the evidence that's in the data can be supportive of the hypothesis, can be supportive of its complement. but it might also be supportive of neither. And so what I'm going to try to present here is that it's this category of supporting neither, this inconclusive category, which is actually where that, you know, let me jump back here. So that what we would maybe expect in these kind of cases is that, let's say like this one. So in this case, this is where the data is pointing to a collision event, right? Because our sort of estimate of that length is something less than 1. What you would expect is that this thing would, you know, really sort of stay down here at 0, would never really climb up to some large value. And when it's climbing up to that large value, this is actually an instance where things should be allocated to that inconclusive category, right? When I have actually very large noise, I shouldn't be sure of non-collision. So what really is going on is that this x equals, x transpose x equals 0.5, this really is inconclusive. And so this should really be going into a inconclusive category and not something that supports the non-collision event. So that's what I want to try to argue, is that there's this sort of third category, and that's where, you know, really that third category, this don't know or inconclusive category, is really where the this inferential uncertainty that we're after, that's where this inferential uncertainty resides. Yep.
So the randomness in this problem, you're not saying it's due to measurement error, it's something else?
There is a
noise that you observe, what is the noise from?
the noise is coming from that this is an estimate of the position, or the difference of the positions in the satellite. So there's a
Sigma in your normal
Yeah.
distribution, right? That is related to the measurement errors?
I mean, I mean, as far as I understand, the measurements in the position and velocity measurements, these are at least assumed to be without measurement error. These get processed into an estimate of the position of the satellite at their sort of closest pass. And now that thing is not observed until, right, so this is an estimate, and it has some kind of uncertainty, just like whenever, you know, when we calculate like an MLE, right, this one has attached a variance to it. So that sigma is related to the variance of that estimate. Right. Okay, so in this, oh, sorry, yeah.
It's kind of a
Yeah.
quick question. If you measure the position and velocity of the satellites precisely, then can you solve the equations for two-particle system, for two object systems precisely, that gives you pretty much combined distribution on probability of collision?
Okay, so if it's, I mean, if there were an equation, then it wouldn't be, I mean, there would be no probability. It would be, it is colliding or it's not. I guess I don't know enough about, so there, I mean, there's something about that they can't solve such an equation. And
I mean, two-body system, then it shouldn't be that hard.
so I don't know enough about this, I mean, the actual like sort of physics of this thing, but
So would you do, so if you knew exactly the positions, you could just calculate. And
Position.
And the positions and
and where
velocities
they're
you
going.
could.
But and then if you have uncertainty about where those positions are, I guess.
Right, but then I thought you have to measure that precise at a time. And then calculating projection to say T prime.
I mean, you did just say there was some sort of measurement error.
I mean, you can't, I mean, I don't know, I'm just guessing based on what is that you never know exactly where something is. You know where it is within an area, within a region, a neighborhood, I assume. And that's where that's part of it.
yeah, so I mean, so the way I understand this one is that this is an estimate of the position based on the data that they have. And so that at some level there is, I don't know whether you want to call it measurement error, or that you're, I guess in a certain way that basically is what it is. I mean, it's that you're not able to see sort of precisely where the things are. I think maybe I was thinking of something else. So these, yes, okay, so let's call this, I have an estimate of the position of the difference of positions, and this is contaminated by some kind of a measurement error. And so from the way this pre-processing goes, that there is some kind of a central limit theorem type of an argument which can justify the normality part, and that there's a sufficient amount of data that's being processed that the covariance structure of that normal distribution is also taken to be known. So, okay, so measurement error, I guess, is the easiest way to think of this. Okay, so I didn't mention this last point. So if this, so I mean, just I haven't told you really what this kind of don't know or inconclusive sort of notion is yet, but when we have more noise, it would make sense that there's this kind of uncertainty would be something more like, I just don't know whether, you know, if I have a sigma which is like 0.9, but I have, sorry, this is the estimated norm is, square norm is 0.9, I just really don't know what that says about the satellites colliding, and especially when the sigma is large. So what I'm trying to say here is that it would actually make sense, whatever this sort of don't know feature is, it would make sense that this don't know feature would be increasing in sigma, not the probability of non-collision. Okay.
Back to that equation you said, given x,
At the beginning here?
that's here.
Yeah.
I just went right back there. Probably bigger than x.
Yep.
Sorry,
Yep.
just
No, it's fine.
question,
Yeah.
but so you're certain that this weird behavior, this weird trend that you see is due to, it's more due to the variance, or linked to the variance than it is to, like, the fact that you're putting a norm for heavily dimension reduced data.
I mean, this is, so I mean,
It's related to the way you're measuring this dimension reduced data as opposed to like a property of this scenario.
so I'm taking the reduction down to the two-dimensional thing as given. So now the norm is being calculated on a two-dimensional thing, not a high-dimensional thing.
Right.
So I've taken the pre-processing out of this. It's just down to this two-dimensional problem.
But
And
it's hard to
then,
understand what this two-dimensional object represents, right? It's complicated to understand what the...
in terms of the bigger picture, or in terms of
In
the...
terms of the problem and the kind of variability that you're interested in measuring, or the uncertainty that you're interested in capturing, right? It's not really easy to interpret this two-dimensional object in terms of the original question or problem, right?
Well, I mean, this is still weird, right? Is that the more uncertainty you have, the more noise, the more sure you are that this norm is going to be large.
Yeah, I guess what I'm just asking is possible that's just a result of using the Euclidean norm instead of maybe a more appropriate norm to use instead.
I mean, I guess I don't. I mean, the idea is that the norm is about the satellites themselves, the physical feature of the satellites. So that what we're saying is that I want to know. I mean, I guess you could. I mean, so like this S, the S that I'm using here, this one doesn't really matter, but the actual S that they would use, this is about in terms of like the sizes of the satellites that are sort of in question. And so what you're interested in is the distance between the satellites. And so what kind of distance, I guess, would make sense? I mean, if these things are spherical, or, you know, like circular sort of shape, which obviously isn't right, but I think that's the approximation that they use, then I guess this particular Euclidean norm makes sense. I suppose you could do other things, but then that would depend on sigma. I think that's what you're getting at, is that you could choose a norm that depends on sigma, but then that's not really related to the size of these satellites and things. I mean, the sigma is something related to the measurement, not about the structure of the satellites. And the collision is something that's strictly in terms of the size and shape of the satellites.
So, just follow up. So is it right to think that we reduce a high-dimensional problem to 2 dimensions, basically 2 orbits, right? 2 spherical orbits, such that each is 1-dimensional, and you have 2 objects occupying almost the same orbit. So you only need a position variable to determine whether they are almost colliding or not. So you can throw away the velocity variables completely.
I think the velocity information is part of the covariance structure. So this is being used in some way. So like it's not just strictly take this 3-dimensional thing and then only focus on 1 or 2 dimensions. There's some kind of other calculations that are going on to take, I mean, ultimately when it starts, this is something which is, it's got the 3 position variables, the 3 velocity variables, and this is for, I want to say that there's actually more variables than that, and this is all getting converted down into a 2-dimensional problem. So there's more details about this in the, it's not really interesting details, but so it's not that you have this positions and velocities and then you're just focusing on 2 dimensions of that, just ignoring part of it, that there's actually some calculation that's done to convert it into a question about a 3-dimensional object and then convert it into a 2-dimensional object, and then that's the result here. So your question about whether they can, actually solve this equation, I'm not sure about. But there is some sophisticated pre-processing that's happening here. That's not simply just. So my understanding is that it can't be reduced to 1 dimension. That it is needed to work on the 2-dimensional space. Yeah. Okay, so I wanted to say a few things here about some generalities about inference, and I think this is helpful in terms of trying to further diagnose what's kind of going on in this probability dilution scenario. So I would make this claim here, which I think is not, well, this is really more of a definition, is that when we think about inference, what we're talking about is conclusions reached based on evidence. And so I think when we talk about statistical inference, this notion of evidence should be front and center. So I want to say here that we tend to think, at least in statistical context, that when we talk about inference, that this is naturally connected to probability, and I think that actually the evidence should be the starting point, not probability. So I want to sort of think about the evidence as being the primitive, the thing that we actually start with. So Harry and I were kind of going back and forth about some things, and we came up with this very grandiose name, which is about the fundamental principle of data science, which it's a very simple statement. The idea is just that if I have some kind of hypothesis and I can collect some data which I believe to be relevant to that, then I make an inference about, I would make a conclusion that's, I would infer this hypothesis A if the evidence to support that hypothesis is sufficiently large, or my measure of the evidence supporting that hypothesis is sufficiently large based on this data that I have. So this is a super high level kind of thing, but I think this makes sense. It's in this sense I want the evidence to be a front and center, to be driving this, not necessarily probability. Or some version of that, yeah. Yeah, I should have dropped in a statement about that.
Yeah. So Cornell is what? Probabilities, low, small probabilities.
Don't have.
Well, I guess it's the equivalent. Maybe evidence by probability.
Yeah. Okay, so it's common to try to apply this, or it's common to employ this fundamental principle of data science with a probability in place of this thing that's called this thing I didn't define, but I'm calling here the measure of the evidence in support of a hypothesis. And so that's exactly what we were talking about in this satellite collision problem. This is also what Harry and I wrote some kind of thing about the election, and this is the same kind of idea as you produce some kind of measure of the probability of Trump and probability of Clinton, and then try to make some judgments based on that. So what we saw in that this probability dilution phenomenon sort of raised some questions about whether the inferences that we draw based on a probability of this type, whether this is maybe this is questionable. And so there's this sort of idea that, well, maybe this additivity, which is special to probability, and I mean that wasn't clear from the conclusions or the points that I made before, but I want to try to argue this, is that the additivity has something to do with, or is somehow inconsistent with this notion of the fundamental principle of data science, and so I need to say in what sense might they be inconsistent. Okay, so it's I mean, certainly maybe even it should be this way, is that inference can be something which is handled case by case, right? So you evaluate the particular situation, you have information in front of you, you want to make some inference based on the problem-specific considerations that are there. In statistics, and I guess also to data science, this is not really the way the process works, and in those contexts, what the focus is typically is on developing some kind of a method that could be applied in similar kinds of situations, but across applications, and that, you know, I want to use those methods to draw some inferences, but I'm not necessarily taking a problem-specific considerations in each case, right? So like in that satellite problem, they are following some kind of a Bayesian analysis, but they do the same Bayesian analysis every time, right? So it's not that they're looking at the data that they have, making some determination that this particular Bayesian analysis is right this time, and then the next time they do a similar consideration and say, okay, now a new Bayesian analysis is appropriate this time. It's the same Bayesian analysis that's done every time, right? So this is not justified as like this is the right way to do it. The point is that it's being justified in a sense that at least, I mean, this is what they're going for, is that the justification for that method is that it should be, their justification is that the method they're employing in that rule is in a certain sense reliable. That when I use this method across different problems, it's, you know, not always going to be right, it's not always going to be wrong, it's going to be right most of the time, that this notion of reliability. Right, and so it's this notion of reliability in this particular sense that I'll define is where there's some trouble with the additivity part. Okay, so in the satellite example, right, we were not getting direct evidence to say that there was going to be a collision. And so what was happening in that case, and that was what the argument I tried to make, was that when the evidence is not pointing towards collision, that additivity is forcing it to then be pointing towards non-collision, and that's what was causing this probability dilution. Okay? And so a way to think about what was going on there was that this non-collision probability was sort of artificially getting boosted. Right, so that non-collision probability was actually not an indication that the data says they're not going to collide. It was some artificial kind of boosting. Okay? And so if we're thinking about the use of this this probability in the context of that fundamental principle, right, that was where we were looking at the magnitude of that measure of the evidence, or the probability. Right? And so if that thing is getting artificially boosted, right, so if that evidence or that probability is large, but not because the data is suggesting it should be large, but because of some other reason, and if this is happening in a systematic sort of way, then this may lead to some misleading conclusions. Okay, so that's this notion of false confidence is a slightly more precise version of this, but the basic idea here is that there are some hypotheses, and those hypotheses will tend to be assigned a large probability, not because there's evidence in the data to support them, but as a side effect here of additivity. Right? And so this is the thing I want to call this false confidence. And so here is a more formal kind of statement of this. So now I'm jumping to a more familiar kind of statistical setup, at least familiar to me. And so the setup here is like this. I've got some kind of a statistical model. So like in the satellite example, this statistical model said that the distribution of x is normal, mean theta, and a variance or covariance matrix sigma that's known. Right? And then when I talk about a hypothesis in this case, this is just some kind of a subset of the parameter space. In the satellite collision example, this parameter space is R2, right? All of those pairs of theta 1, theta 2. Okay, so then I want to define here some kind of a data-dependent probability distribution on that parameter space. So this could be something like a posterior distribution, a fiducial distribution, really anything that you can think of that is a additive probability distribution that's depending on the x in some way. Okay. So then what this the false confidence property says here again roughly, and there's a formal statement coming up, that this guy, that probability for the hypothesis, that guy tends to be large as functions of the data when that data isn't actually supporting that hypothesis, right? So this idea that the actual value of the parameter that this is being evaluated under, that's not part of the hypothesis. So in this context, that hypothesis is false. And so if the theta is not part of this hypothesis at A, then x isn't really supporting it, right, in a probabilistic sense, right? So then that guy tending to be large when that hypothesis is false, right, that's this notion of false confidence. And so specifically what we're saying here is that this guy will exceed so you give me any alpha and you give me any t, then I can find an A for which this inequality holds. So this is saying that probability for the hypothesis A is, if let's say t is fairly large, right, that this would be something where I would likely infer A, right, based on that fundamental principle, right? So this is saying that I actually have large or sort of strong evidence in favor of this hypothesis A, this event where it's bigger than t, but this is that event has relatively large probability even though the hypothesis is false, right? So that's what's happening here. So there's relatively high probability of me making an inference about A, or that I will infer A. That would be a wrong inference in this case because the hypothesis is false, and then that one has non-negligible probability. Okay, so the point here is that I can always find one of these A's. So they're always there. Okay, I'm a little bit ahead of myself. So let me show you this manifestation of this false confidence, what it looks like in that satellite example. So this, of course, is a property of the sampling distribution of things. So I have to do some kind of simulation to illustrate this. So what I'm doing here is something like this. So I'm simulating data that comes from this bivariate normal thing. Here are the mean vector is 0, so they're sort of exactly on a collision course. Okay? And what I'm going to do is I'm going to calculate that Bayesian non-collision probability. Here I called it a pi. I think before I'd call it some p. That's my fault. So this is that Bayesian non-collision probability. And what I want to do is I want to look at the distribution of that Bayesian non-collision probability as a function of x. Right? So this x is one where it's being simulated under a collision event. Right? So non-collision is false. And then I want to see what this distribution looks like. Right? So the one with the green line, where sigma is equal to 2, a relatively large value, this is the one that's sort of the most striking. So you see that this one is a distribution which is pushed almost entirely towards 1. Right? So what does this mean? This green line is like the CDF for this random variable. Right? So if this guy has a CDF which is pushed way over towards 1, that means that across these simulations of x, almost every one of these probabilities was 0.9 or greater. Right? So in all of those cases, you would, I mean, it would be hard to say that if I calculated this non-collision probability of 0.9, that I wouldn't have made a judgment that they're not going to collide. Right? So this is, in 90% of those simulations, I'm getting something bigger. Well, this is, I guess, all of those simulations, I'm getting something like 0.9 or bigger. So in every one of those cases, I likely would have made a determination that they're not colliding. But in every one of those cases, I would have been wrong, because they actually are on a collision course. So this false confidence is getting, what's happening here is that it's forcing, I mean, these probabilities are always large, and not because the data really supports them, it's somehow that the data is not really informative, and that non-informativeness is leaking into the probability of non-collision, and not sort of, there's nowhere else for it to go. It's not supporting collision, and so it somehow is leaking into the non-collision probability, and that's manifesting in this picture where you get virtually all of those probabilities are greater than 0.9, and therefore those would be wrong conclusions and well, yeah, bad situation. Yeah.
If you were, or if I were, or I am, a simple-minded patient, I would be interested in the likelihood of the data given the collision hypothesis, the likelihood of the data given the non-collision hypothesis. If in fact, given the collision hypothesis, the data is really non-informative, then that likelihood is going to be the same on both hypotheses, in which case it's not really going to support non-collision.
So okay, so I think you're suggesting that you want to shift away from the posterior probability of collision to, say, Bayes factor.
Yeah.
This is what you're suggesting.
Right. I mean, of course, the posterior probability will also depend on the prior probability, and that's where you might have biased this in favor of.
Okay, so I mean, so again, this is the Bayesian model that the engineers are using.
That might be a mistake.
Yeah. Well, I mean,
It might not be really a Bayesian model.
I mean, it is a Bayesian model. Maybe it's not a good one. I mean, yes. So sure, there's perhaps other ways that we can assess the hypothesis of collision. I think it's still of some interest, especially because this is what the engineers are doing, to see that in fact they sort of necessarily are always, I mean, they can't not support collision, or sorry, non-collision, based on
that.
Yeah.
I think that your argument is showing that. I was thinking that your overall argument was that it would be much better to understand inference in terms of something like weight of evidence than in terms of probability.
Yes.
And I was thinking that somebody who is committed to probabilistic understanding of how to assess evidence would have a reply to you, but maybe wait until you're done with the whole discussion.
Well, okay, so I think that I mean, this is an argument I think is in favor of that, of what you're saying, is that probability itself isn't the right way to be assessing this. And so then you would say, okay, then and also that's what I'm suggesting, is that some kind of a measure of evidence, sort of a genuine measure of evidence that's not this probability, might be more suitable, right? So I'm pointing out here just the shortcomings, I suppose, of a probabilistic approach of assessing of non-collision. There would be other things, and I'm going to show something else here, not exactly what you're suggesting, but to say that there are alternatives to this additive measure of evidence, and for example, like a Bayes factor is such a thing, is another alternative that's not of this additive type. I'm going to focus on a different type of thing, but the idea is that probability directly may not be the right thing for as a measure of evidence like this kind, right? And so this is a feature of sort of what's maybe well, this is a feature of something that can, I mean, this is a particular thing that can go wrong by using probabilities instead of something else in terms of measures of evidence.
So you show your slide with the end on it.
Yep. Okay, so there are, I mean, there are some kind of things that resemble this kind of conclusion in literature. So these are somewhat specialized things, but there's some kind of a general notion of that joint confidence distributions are not supposed to be marginalized in this way. So this is essentially a claim about a one-dimensional feature of this two-dimensional vector, and that confidence distributions are not intended to be marginalized in this type of way. I mean, there's not really been any sort of explanation as far as I know about why not, except for that it just doesn't really work. And so somehow I think it's this notion of additivity that seems to be explaining that. There are this is a very specific quote by Don Fraser. Has a paper titled something roughly like this. So it's a very potentially controversial sort of claim. So I put quotes around it so you don't think that it's me. It was just that Bayes is quick and dirty confidence, and the argument there is that this kind of notion about, you can construct these posterior probabilities and they're really just meant as some kind of a rough approximation of something in terms of confidence. And that in some cases this Bayesian thing works out pretty well, in other cases it's not, and so a sort of overall conclusion is that it is a quick and dirty confidence. That's was Don Fraser's conclusion. So in terms of this specific result, this false confidence theorem, so I mentioned already this is about existence of a particular hypothesis, and so it just says that it's an existence result that there exists such a hypothesis where that property where that property holds. It doesn't say that, of course, that every hypothesis is, I'll say here, afflicted by the false confidence, and it also doesn't say which ones they are. Okay, so there are trivial ones that you can identify basically automatically, and those kind of trivial things would be, for example, so very often these probabilities are like continuous measures. They have densities with respect to like a Lebesgue measure, something like that. So of course I could take this A to be the complement of a measure 0 set.
So is there, in that formula down there, is there also a X is fixed for every alpha, every P, and every X?
This is a probability with respect to the distribution of X. So this is a statement about the random variable pi X of A as a function of X. Yeah. Yeah. Okay, so there is a trivial choice of an A which would always satisfy this, and it would be one where you say, okay, let's say that my posterior has a density with respect to Lebesgue measure. All right, so then I can go to that two-dimensional space where the parameter lives. I find the complement of a Lebesgue measure 0 set, and then that one will always have pi x A equal 1. Right, so then this would be automatically satisfied for such a thing. So of course this wouldn't be interesting if that was the only kind of hypotheses for which this one, I'm not out of time, right? Okay. Yeah, so that's not that's not the only kind of hypotheses for which this kind of thing would happen. Otherwise, this wouldn't be interesting. So, I mean, we actually saw already that in that satellite collision problem, that was, of course, a non-trivial type of hypothesis. In fact, it was something that was of practical interest. And so in that case, we were also seeing this kind of false confidence feature. Okay, so it would be nice to be able to identify which hypotheses are the ones that are afflicted by this, because then of course you would very easily could say, okay, let's work within this Bayesian type of framework, and then we can just say, well, don't apply it to these kind of hypotheses, right? You just list out the ones that are afflicted, and then you say, well, don't apply them to those problematic ones, only to the non-problematic ones. And so, I mean, that would be nice. So I think where you run into some trouble is that, we're often talking about some kind of relatively high dimensional kinds of problems. And so, one that I had seen some things before, and this is just sort of just sort of a quick example, but, there's, people do some kind of thing. So in my department, there's a lot of people who work on spatial statistics. And so they do some kind of things like, They want to build these sort of spatial models that sort of capture space and even sometimes time, right? They're sort of capturing these very complex type of structures in the data. And they may do some kind of thing like, okay, I'm going to fit some kind of a Gaussian process that has a certain kind of covariance type of function. And then maybe at the end what they want to do is they want to make some kind of statement about the certain kinds of a spatial correlation function, right? And so this would be some kind of complicated nonlinear function of these parameters involved in this very high-dimensional problem. And so it seems very difficult to say, to be able to make a determination that, say, a hypothesis about maybe that correlation function would or wouldn't be something that would be afflicted by these kind of things, right? So this is a very complicated nonlinear type of object, and so it seems virtually impossible to make a determination that, that in a particular problem like one of those complex high-dimensional ones, that you could make a judgment that, okay, this particular A is one that's safe and this particular A is one that's not safe. So if this kind of determination is a problem, how closely or how tightly should we hold on to this notion of additivity? Okay, so the next sort of thing is, so let's suppose that I wanted to avoid, right? So I'm concerned about this false confidence notion. Let's suppose that I want to avoid it. If I want to avoid it, right, so that the only condition in that theorem was that I was measuring the evidence based on something additive. So if I want to avoid this false confidence, then I have to go non-additive. That's the only thing that I know based on the theorem. Okay, so we can start to ask some kind of questions about this going non-additive, and we can say things like, maybe first is that, does something non-additive actually make any sense anyways? What kind of alternatives are there to the more familiar type of additivity? And okay, so suppose I wanted something that's non-additive, how do I actually get such a thing? Okay, so I mentioned this a couple times already, is that this, what I'm talking about here, this sort of notion of inferential uncertainty, which I argued was not captured by the kind of probability calculation that was done before. What this really boils down to is inability to classify evidence as going to the hypothesis A or to its complement, right? So that means that there's, I somehow have this kind of inconclusive evidence that I don't know where it should go, right? And so in this satellite case, right, when there was large sigma, right, I could have have data which is consistent with collision and with non-collision, right? That sort of like the norm of x squared was 0.9, right? This is not really, especially when the sigma was large, this is not conclusive of doesn't support collision or non-collision. It's not really clear where it should go. Okay, so if I were to be thinking about something which is additive, I have some kind of a measure of evidence which is additive, right, which would be something like this, right? Of course, this is just for A and A complement, but more generally would make sense how everybody knows how to adjust this one for general A and B. So what this one suggests, if I had something if I had a setup like this, right, this is suggesting that any evidence that supports the union of those two things has to support exactly one of A or A complement. That there's no gap, right? There's nothing that's inconclusive. It either goes to this or to this. I can always make that determination, right? And so the point up here was that even in this satellite type of example, right, that's just not possible. There are certain cases where evidence is inconclusive, and I just don't know what to do with it. So I'm arguing here that there needs to be some other category to which you can allocate this inconclusive evidence. So we have the expert in super-additivity is here. So one alternative to additivity is what's called the super-additive, and the super-additive property is something that looks like this. Says that the evidence to support the union of two hypotheses is no smaller than the sum of the two individual measures of evidence. And so here I've written this in terms of some disjoint things. So this one would handle the case, right? So if B were equal to A complement, right, then this would handle that case where the evidence doesn't support, or evidence supports neither A nor A complement. So the point is that I could have the evidence in support of A or A complement. That could be large, right? That would make sense that maybe that's large, but that I could have evidence to support A and evidence to support A complement, and both of those could be small. and this inequality would still hold. Okay? So
You don't really need evidence to support A or A complement.
well, that's right. So that, I mean, we would expect that whatever data I have, this one would be large for if this is A or A complement. So that this guy could be large, but these two guys individually could be small. Right? So that leaves open some kind of space for some extra kind of category which could capture that gap between maybe some large value here and a sum of two small values there. Okay? So Glenn here has a book about these kind of super-additive type of measures, and there he calls these ones belief functions, and I'll use this, when I'm talking about these super-additive guys, I'll use the BEL, the belief, for this. Okay? So it is possible, for example, in this satellite collision example, if I have A is non-collision and A complement is collision, then in fact I have both of those things could be small, right? And we would expect something like this, is that when the sigma is large, I don't really know what to do with the data. Right? The data is not informative, I don't know. And so it ought to be that the evidence to support A and A complement both are small. Okay? So that's the claim. Okay, so if I were to have this super-additive type of setup in terms of, let's say, these belief functions, then I can define a thing which is this complementary function that Glenn called here the plausibility function. And this is, I think I typo here, this should be belief in A complement there. So 1 minus the belief in A complement is the thing called plausibility. And that super-additivity property says that the belief is no bigger than the plausibility. So I have this kind of notion of a kind of a lower bound, a sort of lower notion. This is sort of a direct measure of the evidence my direct evidence to support A, and this is the stuff that is not inconsistent with A. Okay? And you could think of this difference as this sort of measure of the inferential uncertainty or the inconclusive evidence, or this thing I called here that actually Art Dempster called the don't know. Okay? And in terms of this plausibility, there's actually something nice that says that, you know, if I turn that fundamental principle of data science around and I express it not in terms of evidence or belief, but in terms of this plausibility, then it says that if plausibility of the complement of A is small, then I would infer A. So this is now almost exactly like the Cournot principle, and actually is very closely related to things like p-values and confidence and some of the classical statistical things. Okay, so this is the last, well, I have a few things to say about this, but this is the last topic is, okay, now we've kind of set up this idea that, okay, I can go beyond these additive measures of evidence, and that one, you know, so the false confidence says you can't be additive. If you want to avoid false confidence, you can't be additive. And I've suggested here one kind of non-additive measure of evidence. And so there's a natural question as well, what good is this? Is that actually, I mean, just going non-additive doesn't guarantee you've avoided false confidence. There's something more to it, right? So what I want to say here is about how to actually get one of these non-additive measures which will avoid false confidence. So that's the last thing that I want to say. So this is a new, relatively new setup, so I'll just say a few sort of general comments about this. So in this, what I'm calling here, this inferential model framework. In this inferential model framework, the starting point is some kind of a statement like this, which is essentially a statement about I mean, let's think of this as a more general version of that x equals theta plus z from the previous, the satellite collision problem. Okay, so in that situation, we had x equals theta plus z, and the z had a known distribution, which was a bivariate normal with mean zero and known covariance function, or covariance matrix. This one here is just a more general version of that. I've used the symbol u instead of z. It's just that there is x is equal to some function of theta and this u, and that u has a distribution which is known. Okay, so also this function here, a, is also something that's known to me. Okay. So what is the main intuition behind this inferential model sort of framework is that if I actually could see the u, right? So thinking like in terms of that satellite collision example, if I saw z, then I would just solve the equation for theta and I'd be done. Okay. So now, of course, we don't actually get to see the z, So I can't actually solve for the theta in that way, but I can transfer this problem of inference about this unknown theta to making a statement sort of like a prediction about that z that I didn't observe. Right here I'm writing in terms of u, I should have written z. So if I could do a good job of sort of, quote, predicting or guessing where that unobserved value of z is, then I could effectively do a similarly good job of solving the equation to get to the theta. Okay? So what's the main idea here is that I would really like to know what is the value of u, or z, which is attached to the x that I observe and the theta I don't know. Now, I don't actually have access to that z or that u, but I have some information about that z in terms of its distribution. Okay? So what I want to try to do here is to design a random set. So this is a random set that's defined on the space where the u lives, or z. Okay? And I want to design that random set in such a way that it's going to do a good job of capturing most z's. Okay? And so obviously I have to specify this random set, but the flip side is that, well, if I specify this one in a reasonable way, then I'll be able to say some things about the final properties of my kind of belief function. Okay, so but the main idea here, I would just want to make sure, well, hopefully make sure this is clear, is that there's this unobserved z or unobserved u that's there. If I knew that thing, then I would just solve for the parameter done. Right? When I see the data, I would solve for the parameter, I'd be done. There'd be nothing to do. Okay? So now I don't actually have access to that z or that u here. Okay? And so what I'm going to do is I'm going to try to design a random set which is good at predicting values of u or z. So guess or predict, I don't really know what's the right word. We call it predict because guess is a bad. That doesn't sound very scientific. I actually like guess better, but anyway, so this is, call it some notion of predicting, and that there's this unobserved z or unobserved u that's sitting there, and I would like to know what that value is. I can't observe it, but I know something about the process that created it. That was this known distribution that's here. And then I want to design a random set which is good at hitting those kind of targets which are generated from this P of u. Okay. So something like a singleton random set, say like sampled from the same PU distribution, this would represent that unobserved value in a distributional sense, but would never be correct. It would never hit that thing exactly. But what I really wanted to do is hit that thing exactly, because if I can hit that thing exactly, then I know the corresponding theta, I know where it is. Right? So if I hit that u or that z exactly, then I know I have x, I have captured that z, so my solution for theta would be right. I would at least up to some kind of, within some set. Okay, so this random set allows us to some chance of actually getting that unobserved z exactly, and therefore getting the actual theta exactly. Right? But this random set is not something that I have, I have to think about its distribution. So I can't say I got it right or I didn't get it right on any particular instance because I don't know the u or the theta. Right? So this random set gives us some extra flexibility to define some kind of a measure on that parameter space. And the idea is that hopefully this new measure, which I'll say here in a second, but is automatically super-additive. But that by a careful choice of this set, I can do a good job of sort of, let's say, avoiding the false confidence that we saw before. Sorry.
Can the distribution of the random set depend on the data or not?
So it's, I would say it is possible to do that. That's sort of a, that's a sort of a fine point. So I would say that it can depend on that thing in some sense. It's typically not to take it to depend entirely on data, but often it can depend on some. So, like for example, a thing that we have done before is to have the random set distribution depend on, say, like an ancillary statistic that's inside of the data set. So that would be something that could happen in certain cases, but that I wouldn't just generally advocate for dependence of the random set on the data itself. Okay, so here is some kind of mechanics about how that formulation goes. So ignore the union here for a moment. So this would be those thetas that satisfy, when I was talking about solving the equation, this would be, so ignore the union for a moment, this would be the set of all those solutions. Often would be a singleton, but this is for a particular u. What I'm taking now is my set of solutions is now a random set, and it's a union over this random set of u's. Okay? So the point here is that if that random set is good at capturing the unobserved u, then this random set is good at capturing the true theta. It has to contain that, because if this S here contains the actual u that I don't have access to, then the true theta is a solution to that equation with the actual u there. So therefore, this guy has to contain the true theta. Okay? So I've expanded my set of solutions to include, to be based on sort of a random set of different u's. So now this now gives me a random set of thetas, and a way that I can assign belief to a particular hypothesis would be to ask what's the probability that that random set is consistent with that hypothesis. So that is that all of my solutions to the equation belong to this hypothesis set A. Okay. And again, if that random set is good at capturing the unobserved u, then this theta x of S is another random set, and it's going to be good at capturing the actual theta. So then this, in a sense, I mean, of course it depends on the choice of this S here, but that this is, in a way, is capturing the kind of uncertainty that we have. I can have some kind of guesses about where I think this theta is based on the data I've observed. And this one is sort of intended to capture that uncertainty about where exactly it is. But if all of those guys are consistent with this hypothesis A, then that's evidence to support truthfulness of A. And then I can do a sort of similar calculation to get to a plausibility function based on this this kind of this random set in the parameter space. So I've left off a lot of details here. I tried to summarize what I thought were mostly the sort of the main ideas, but there's a lot of details. So I have here a commercial for a book of ours from a couple years back. So I won't say. It's annoying if I say too much about it, so I'll skip over that. So in terms of the sort of technical details about how to specify this random set, there's a number of those details are in the book and some other kind of papers. There's still some questions about sort of how to do this in a optimal sort of way, and I'll have something to say about that at the end. Okay, so what I want to, so now we're kind of wrapping things up. So when we started this adventure from additivity, what was the motivation was to be able to avoid false confidence. Okay, so now nothing that I've said so far about these super-additive measures would indicate that the false confidence is now avoided. Right, so there's something more that needs to be said here. So this really boils down to a certain choice of this random set, and I mean I can say a few things about it. I didn't put it here in the slides. This sort of depends on timing. But for a suitable choice of that random set, and so the book talks about what does that actually mean, suitable choice, then that corresponding construction of a belief function like this will lead to, I mean, it will have this particular property. So this one is saying that this is now my measure of the evidence in support of this hypothesis. This is an event where that, I guess the thing about like the alpha is small. So then this would be a case where there's strong evidence to support this hypothesis. And what this inequality is saying is that the probability of having strong evidence to support this hypothesis would be small. And since the theta is not part of that hypothesis, it means that the hypothesis is false. So this is a case where I'm asking what is the probability or the evidence being, or sorry, weight of evidence being assigned to this false hypothesis. And I'm asking the question, this is the event where I'm assigning high weight of evidence to that false hypothesis. And the claim here is that that probability will be small, right? In the sense that if I pick a small alpha, then this is a large evidence, and this is large weight of evidence, and this is small probability. Okay, so this one it actually can hold no matter what A you pick. So this sort of defines, this construction is something which will let us avoid the false confidence in the sense that no matter what A I pick, whatever hypothesis I pick, then I can achieve this inequality that says that I'm just not going to get it wrong too often based on this particular kind of construction. Okay. So I wanted to go back to that same kind of setup with the satellite collision. So this is, everything here is the same. Actually, I've drawn the probability curves on there again. I don't know, they're gray, lighter colored, so they maybe are harder to see. But what's drawn in this picture, it's the same four settings, the same function of sigma. So what we see in this picture, so this is the case when there was, when the data actually points towards collision, right? Because the length of the estimate is smaller than 1. And so what we can see here is that, so the gray line is that probability that I showed you before. So there's actually two new lines that are drawn on here. There's this one, this dotted one that's actually strictly 0 here. And then there's the solid one which has this kind of curve. So the dotted one is that the belief function. So this is the belief in non-collision as a function of sigma. This is the solid line is the plausibility of non-collision as a function of sigma. And what is the main feature that I want to highlight here is that the difference between plausibility and belief, which is always non-negative, is actually increasing in sigma in all of these cases. Right? And so we understood that more noise, higher sigma, meant more inferential uncertainty. And so this idea that the spread between the belief and plausibility is increasing in sigma, that matches up with the intuition that we would expect about more noise means more uncertainty, doesn't make probability of collision or probability of non-collision higher. It means that it's harder to distinguish between them, that there's this notion of more, it's more inconclusive the larger the sigma is, and therefore we should see more of a gap when the sigma is large between the belief and the plausibility. And that's what's happening in all four of the panels here. In some cases we can't, of course the data never directly supports non-collision because my estimate of the length is smaller than 1. So there's actually no way for this data to support non-collision, and that's why the belief is always 0. But non-collision becomes plausible, actually becomes highly plausible when there's a lot of noise. Okay? And this is one where we see sort of the opposite behavior, is that when the estimate of the length is relatively large, that means that the data is pointing towards non-collision. Okay? But as it becomes more, as we have more noise, there's more uncertainty, and so we see actually the belief in non-collision actually decreases to 0, whereas it stays, sort of fully plausible of non-collision, which makes sense because of our estimate is bigger than 1, so we can't rule out the possibility of non-collision. We just believe in it a lot less when the data becomes noisy. Okay, and this is the corresponding version of the other figure from before, looking at the distribution of, in this case, the belief function. This is distribution as a function of the data for the particular, in this case, this is the non-collision event A. And so the data is being simulated on a collision course. That's the mean vector is 0 here. So remember what that theorem about this belief function said is that, in sort of simply stated, it says that it's stochastically no larger than uniform. That's the thing here. What that actually means in terms of a picture is that this empirical CDF that we're drawing should always be above the diagonal line. Okay? And so we see that actually in this picture, that the diagonal line is the uniform sort of reference, and that we never actually go below that uniform line. And that means in this case, right, so when these guys are jumping up, means that actually in a number of these cases, the data that I simulated, those beliefs assigned to this false, the non-collision hypothesis is false in this case. This kind of thing, sort of quick jumps, means that there's a lot of these belief values are small. Right? And so since the hypothesis that we're evaluating is one that's false, we want to assign small belief to that. So having this kind of pile up towards 0 means that we're not making too many mistakes. Okay? Okay, so I think this is basically my last slide. So I just wanted to say, kind of just to summarize. So this satellite collision example is actually a nice example because it's except for the physics that I don't understand, it's a pretty simple example and actually reveals something kind of weird is going on here, that these non-collision probabilities are not really capturing the kinds of uncertainty that's there, in the sense that sort of non-collision becomes almost guaranteed according to these probability calculations, even though the data is very noisy and really non-informative. So this notion of a false confidence, really says that, there are certain kind of hypotheses which are just getting assigned high probability really artificially. That this is something which is, according to the theorem, seems to have something fundamental to do with the additivity of these probabilities. And so this last thing I mentioned about this inferential model approach, this one provides a way to get one of these sort of genuinely non-additive measures, and that by the construction of this thing, which can be carried out, and I showed you a case where it was done, those calculations were done based on these random sets, that for a suitable construction of this random set, those belief functions that you get are guaranteed to avoid the false confidence property. So that was, really what was driving the construction of these things, even though at that time we didn't know this notion of false confidence. What we were trying to do was to make sure that we can control making mistakes too often. That was really part of our construction. So some kind of questions here, it's natural to leave with some kind of open things. A question we could try to answer would be something like, for a given problem, what kinds of hypotheses are those that are afflicted by the false confidence? As far as I know, and so we only have sort of basic understanding of this, is that it seems to have something to do with nonlinear functions of the parameter, and certain kinds of nonlinear functions that sort of give that hypothesis set as somehow is a bounded set in the full parameter space. So this, I don't have really a precise understanding of this yet, but it seems to have something closely to do with nonlinearity of the quantity of interest, and maybe something else. Here I was sort of selling this idea of a super-additive type of measure, but there are other things. So for example, like you mentioned the Bayes factors, that's another way to measure evidence. Not super-additive, it's not additive, it has some other kind of features, right? There's other kinds of measures more generally. Are those things suitable? Is there ways to say that those things are going to avoid some kind of false confidence issues? I don't know. Here I just showed you one kind of a basic solution based on this inferential model formulation. I don't at the moment have what I would consider to be the best formulation. I have one that I think is reasonable. One that would be best would be maybe resting more tightly towards this diagonal line, because being closer to the diagonal line means you're going to make fewer mistakes in the other direction, right? So this is about making mistakes when the hypothesis is false. Right, but there would be other cases where, when the hypothesis is true, I want the belief to be large. Right, so I'm kind of trying to balance these two cases. Right, I want belief to be not too large when the hypothesis is false, and I want belief to be large when the hypothesis is true, and so I would like to try to balance that, and one way to do it would be to try to be as close to that line as possible. So here I have not achieved that in the sense that they're not very close. And so that's one thing of interest, to try to figure out what is the sort of the ideal or sort of optimal formulation to this. And maybe a last thing is about, I showed you this thing about the satellite collision, and I think that's a nice example. It would be interesting also to identify maybe other cases where perhaps this false confidence is sort of lurking. They're there. Well, okay, I have one other thing I might say about this, but I'll skip that. So anyways, there are some, it would be interesting to try to identify other examples and maybe try to understand this better. So maybe I'll stop with that for now.
So you're on a collision course with Bayesians?
I'm not, I just want to understand things, because I guess for me, I think it's, there's, when you talk about, the Bayesian formulation is saying that you can get to this posterior distribution, and that then you basically can answer any question based on that. Now that sounds nice. I guess, in my opinion, somehow you can't expect the data to be that informative, right? Because when you have this distribution, this is a thing which is, it is defined on a sigma algebra of hypotheses, right? And there's tons of things in that sigma algebra. And how can the data that you have that's of sort of limited resolution, right? How can that be informative about every hypothesis in the sigma algebra? It can't. So somehow that, if you say, okay, I'm focused just on some nice hypotheses, then I think that perhaps this is fine. But that in general, I think it makes sense to expect that there are some hypotheses for which the data is not informative, and that perhaps this sort of manifestation, or whatever we're seeing here with this probability dilution and false confidence, maybe that's just a manifestation of the inability to speak informatively about every hypothesis based on limited data. So
that's been the complaint about Bayesianism from the beginning. It makes you involves you being over opinionated when you don't have any evidence.
I don't know if that's been highlighted in this particular way, right?
But
yeah.
It was an interesting way.
Yeah.
Even the theorem that says that such a problematic hypothesis A always exists, but it doesn't say whether or not it's going to be a trivial case, right?
So there always are trivial ones,
right? And
there might not be any non-trivial ones in a particular case, but you don't know. So like in the satellite collision, I've showed one example where there is a non-trivial hypothesis for which something is bad. Now, in a particular problem, you have no idea, right? I listed that as one of the questions, is can you identify which ones are the ones afflicted? At this point, I don't know really anything except for trying to sort of think about what was weird about this case, which was that it's like you're interested in this sort of a nonlinear function of the thetas, which that norm is a nonlinear function, and that somehow the event that you're interested in, right, this is, okay, non-collision event is the other way, it has something to do with that, so if it were, let's say, a hypothesis about theta 1, like that theta 1 is less than 6, right? This would be one where it's sort of unbounded in both directions. But this thing about the norm, it highlights like a circle and then an outside of that. And so one of them is a bounded thing and one of them is unbounded. And I think it's this something about nonlinearity and then something being bounded and unbounded. I think that's related to what's going on. I don't have a precise statement of that, but that's my understanding at the moment.
Just clarification, for the theorem you have for the IM model, does it solve for the trivial case as well?
Like trivial?
Now we're thinking about the trivial case of false confidence intervals where
you just have the complement of some, basically an empty set? Yeah.
The hypothesis.
Yeah, so this is for
You didn't put that those two formulas, the int and the soup one, you didn't put them on the same slide, so it's right there.
Yeah, sorry about that. So maybe first about this thing here. So this is, it holds for any A, including A's which are, you know, if you talk about A's, they could be full Lebesgue measure, zero Lebesgue measure. So what actually is happening here, so let's say that A were something like, if A were the complement of, say, a measure zero set, right? So that would be like that trivial case in the false confidence setup, right? So then this guy, okay, what did I say? This is the complement of a measure zero set. Yeah, so this would be effectively the whole space. This guy, I mean, so if you pluck out, okay, I'm having some trouble here, but so let's say it's the full space, right? So that there's nothing plucked out. So then this guy would always be a subset of the full space. So then the belief would be equal to 1, right? And so then this guy, okay, so this would be what? Well, okay, so then, yeah, there's nothing to say. Okay, so that's not very interesting.
It's still true.
Yeah, it's still true, but that's not very interesting. Okay, so, okay, that's not very interesting. So how do, okay.
Suppose A is a complement of theta, so it includes everything except for theta.
Okay, so yeah, so if A is complement of the theta, so then this would be true. Then if we go back to here, okay.
Well,
Yeah, so okay, so this,
in that example, you're going to choose S so that delta is 0.
yeah, that's I guess what's trying to make happen, right? So the oh shoot, okay. So. Yeah, so I mean, what this one will, I mean, very often look like is, so let's take that, I can maybe write a little bit here. Let's maybe say like this. Okay, so in this particular case, what, okay. Okay, so how this one will work, I can maybe write more, but let me maybe just say like this. So it's not any random interval, but it's a particular random interval around 0. That's actually how, or sorry, random, in this case it's 2 dimensions that we were talking about. So it's a, it's like a random disk around this one. Okay, so if the so this is a random disk around 0, and so then when I look at that theta x of S, that's going to be a random disk around x, and the x tends to be close to theta in probabilistic sense, right? So then this thing right, is actually going to, I mean, it's going to be near, again, in a probabilistic sense, it's going to be near theta, right? So then if it's near theta and it's so centered around x, then it probably has theta in it, okay? And then if you then ask, well, what's the, look at this case, sorry, where, so if this is the complement of theta, right, then, and since this guy tends to have theta in it in some kind of probabilistic sense, then this event is not going to be satisfied. So then this guy tends to be small. So then the probability that this guy is bigger than some alpha would also be small. Yeah, so it was a pretty lousy explanation that I just gave, but
just a comment. On your last slide, you mentioned about super-additivity and whether that's desirable or not. I guess I'm curious about, you talk about belief and plausibility play them off each other. And I'm wondering, so it seems for one that this second principle, this Morneau-like principle, that small plausibility in the complement allows you to infer A, seems to be tied to super-additivity.
yeah.
And I wonder I wonder the extent to which that would be, you would want to relax that in the sense that based on the data, just because the complement is plausible or is implausible, should that lead you to believe that, I mean, can't both A and its complement be implausible based on the data? And what would that lead you to say, I guess? I mean, I understand why it's there, but is it conceivable that a situation might arise where it's such a strange observation?
I mean, if belief in A and A complement are small, then actually the plausibility would be, yeah. So then it would be above that cutoff, right? So what had to happen was that plausibility had to be small in order to make an inference, and so plausibility in the complement being small means belief in the thing is large.
I guess I'm just curious. Is it conceivable that you see something and you ask about A and you say, well, that doesn't. A seems to be implausible in light of the data, but at the same time, the complement seems to be implausible based on the data, and I guess you would just maybe think that
I think that you can't. I think things being implausible is that's a hard judgment to make. Things being believable is something that you can rule out, right? So if both things are plausible, so I think that I think maybe both things can't be plausible under super-additivity. Wait.
That's what you want to
Yeah. Yeah.
say. Because both things being plausible, implausible is the same as both things being believable.
Yeah. Right. Right. Yeah.
So I was interested, it's interesting, the professional situation of your, you call them conjunction analysts?
Yeah, that's I think that's an old name for these things. I think maybe now they more would go by collision analyst. So this was my collaborator who is the one who knows something about these, like the actual physics and all of that stuff behind it. He works in this kind of aeronautics stuff. I mean, he told me that conjunction analysis is an old name for this, and so I don't know. Like the paper has attached to it conjunction analysis something, so I use that term here. But I think collision analysis makes more sense.
I think there's something professional going on here, which is that the conjunction or collision analyst is expected to give a report based on this particular data. If you had a Bayesian that was just, not just looking at this particular data, but starting point is, well, collisions aren't very likely. Then he wouldn't have any problem that collisions still aren't very likely. We just ignore this data. but if you're asked to give a report based on this particular information, I recall, over the years, some of the people that were most interested in belief functions and actually probably used it the most were intelligence analysts. And they're in that same situation. They're being asked to, give a report on what you found out.
Yeah, yeah.
Not on what you thought in the first place.
Yeah.
So that's the kind of professional situation that drives them towards this kind of
Yeah, yeah.
way of talking.
Further questions? Okay, all right.
Okay,
Thanks a lot.
cool. I was telling